Hello guys, welcome to Thursday. This will be the video for the lesson today, and your assignment will also be in the same folder as this video, as well as the notes that you will need for today. Also a reminder that you can access the assignments on the right-hand side of the main course page. So however you get to the assignment is awesome. Just make sure you get it done before midnight. All right, so I'm going to switch over to my document camera so we can get started for today. So we spent the last 2 days talking about angles, and we talked about some relationships between angles yesterday and different types of problems that we could solve with them. Well, today we're going to talk about line segments and different kinds of problems that we can solve with them, and one type in particular that's going to be pretty important to this class. Now, line segments are pretty straightforward, so I don't think we need a whole day just to talk about what they are. We already did define them on Monday. So I'm going to dive right in and talk about how they relate to geometry as a topic. So one of the biggest things with line segments is they relate directly to one-dimensional distance. So what I mean by one-dimensional distance is probably the first way you ever learned how to do distance, and also how you learned to count things on a number line. So just for a quick example, if I have a number line with 6 marks from -2 to 3, and I asked you, well, what's the distance between -2 and 3 on the number line? Now this works a little bit differently than just doing an addition or a subtraction. It has one extra step to it, but whenever we have the visual, we could just count the numbers. Okay, well that's 1, 2, 3, 4, 5. So it takes 5 increments to get from -2 to 3 on the number line. And that represents the one-dimensional distance between the two numbers. So just to be very, very particular, there is a formula for finding one-dimensional distance, but don't let that word scare you. Essentially, you take your first number and subtract your second number. But distance always has to be positive, and so we add something called absolute value lines. So here, -2 minus 3 is -5, but we can't have a distance of -5. That doesn't really make sense to us. A distance always has to be a positive number. We can't really go inwards distantly. And that's where we get 5 as the distance. Now again, with this model, we could just count it. All right. So we can use that same concept to find lengths of line segments when we're dealing with them in one dimension, meaning on a number line. So let's find the lengths of AB, BC, and AC. So I'm going to draw a number line. It might take you a moment to copy it all down. That's okay. But over here, we're going to have point A at -6. And here I'll put point B at -3. And lastly, C at 5. This doesn't have to be for scale or anything like that. This is just for our notebook. So if we wanted to fill in the marks to be able to count, we could do that, but that takes up a lot of our time. So it might be quicker for us to use the absolute value method. So for line segment AB, finding the length means finding the distance between -6 and -3. And if we want to be super duper technical, we can do -6 minus -3 in absolute value marks. The double negative will turn into a positive. And then the difference between -6 and 3 is -3. And the last step, the absolute value marks, turn that -3 into a +3. Again, that's a lot of steps. If you can do it in your head, absolutely do it in your head. I'm just showing all of the steps just in case someone isn't quite there yet. So then let's look at BC. So this would be the segment between point B and point C. So again, you take one point and subtract the other in absolute value marks. That'll give us -8. But again, distance can't be negative. So really we're saying there's 8 little tick marks to count between -3 and 5. Lastly, it wants us to find the length of AC. So that's going all the way from A to C, all the way from -6 to 5. So again, -6 minus 5 is -11. And then we make it positive. Now let's take a moment and see if there's something we notice about AB, BC, and AC. And I'm going to use some colors. I got to pull them out though. Pink, blue, and sea green. So from A to B, it's there in pink. From B to C, it's here. And then from A to C would be this whole length. Well, if I'm putting AB and BC right next to each other, they're making up the entire length of AC. And what do we notice about their lengths? 3, 8, and 11. Well, 3 and 8 together make 11. I think we're onto something here. So just for a little note for ourselves, notice how AB plus BC equals AC. That is 3 plus 8 made 11. Well, that's a little something called the segment addition postulate. So segment refers to a line segment. Addition, of course, means you're adding. What about that last word? Postulate. Probably have never heard that word before, and I sure hadn't before I got to geometry class in high school. That's a very special word for geometry that has to do with, how do I put it? Like a rule almost. I probably should have had the definition on hand for this one. It's been a while since I've defined it. So a postulate in geometry is a statement that is taken to be true, and it serves as a premise or a starting point for further reasoning or arguments. So to put it simply, this is just something that we're always going to assume is true and works, and we can build things off of that assumption. And so far, the assumption hasn't failed us yet. I know in real life, making assumptions isn't always a great thing, but In math, we have very special assumptions called postulates or axioms, and we're allowed to use those all the time. So, the formal definition or wording for the segment addition postulate is as follows. If 3 points are collinear, remember that word from a few days ago? That means if 3 points are together on a line, and B is between A and C, then AB plus BC equals AC. So essentially that's saying the two pieces can make up the whole. And we'll put a little illustration to this because I always like to have a visual for all of the things that I do. So here we have A, B, and C. It doesn't matter where B is in between A and C. B could be all the way over here, could be all the way over here, could be perfectly in the middle. As long as it's somewhere in between those 2 points, the segment addition postulate works. So I'm going to color from A to B in blue. And then let me get a color for B to C. Lots of marker noises. So if I take AB and BC and I line them up and I put those measures together, we end up with AC. All right. So let's get to some examples of how we use the segment addition postulate to help us solve problems in geometry. So for example 1, I want to think, do I want you guys to have to write all this out? Yeah. So more often than not in geometry, you'll be given a problem in words, and you'll have to come up with a picture for it. So we're going to practice that while we have something relatively simple to work with, like segments. So if X, Y, and Z are collinear points, and Y is between X and Z, find the length of XY given, no, XZ, my bad. We're finding the length of XZ given XY is 4 and YZ is 10. I'll give a moment. You can pause if you need to catch up on writing that. But I'm going to move along to keep the video shorter. So if you're able to do this problem in your head, that's fantastic. But as we get further into the course, these things will get a little bit more complicated and less easy to do in our head. So I'm going to show the process of, well, what do I do if maybe I don't quite know how to tackle this problem? So let's start off with the fact that we're dealing with 3 points, and they're all collinear, meaning they all fit on a line together. So I'm going to start by just drawing a line. And I'm told that Y is between X and Z. So I know all 3 points are on the line. and y is in the middle somewhere. And since I'm just drawing this for my own understanding, I don't have to guess where y is in the middle. I can just kind of put it somewhere. Because again, these things don't matter if they're drawn to scale. They're just for our own personal understanding. Then I know that I'm given xy equals 4, so I can go and label 4. And yz equals 10, so I can put a label of 10 there. And it's wanting me to find the length from x to z. And again, I messed up there. It should say from x to z. Now, based on our postulate, one piece plus the other piece will give us the length of the two pieces put together, literally. So for this problem, we just need to figure 4 plus 10, which should be basic enough. Boom. 14 is the length of xc. I just wanted to model that process for you guys of how you kind of tackle these things piece by piece. And again, the math for this one worked out to be pretty simple. So let's take it up just one step. And to save on room, I'll try to write this a little bit shorter. So we can assume the same process where L, M, and N are collinear. And M is between L and N. And what you're given is Mn equals 17 and Ln equals 28. So we don't want to immediately jump to the conclusion that we add these two together and we're done. We have to pay attention to the letters they're giving us, which is why even with problems that seem simple, I always like to draw something out. I'll do that over here this time. So on my line, I know L, M, and N are all together, and M is in the middle. Let's do L, M, and N. And now I want to look at what I'm given and figure out from there, okay, Mn, so from M to N is 17, and then Ln, so they actually gave me the whole length, is 28. And I forgot to write this in the question, so I'm just going to put an X here. We're going to be solving for Lm. Now here's why I said we didn't want to wrongly assume that we just add the two numbers together, because we already have the total. We're trying to figure out one of the pieces. So we're actually going to go backwards. So it may be the case that piece 1 plus piece 2 equals total. And we're used to, in the above problem, it was 4 plus 10. Well, that's easy, that equals 14. But now we have piece 2 and our total. So we actually have to subtract this time. So 28 minus 17 will give us x equals 11. More often than not in geometry, you're going to find you have to work backwards, which is why you want a really solid understanding of each piece. Because if we wrongly assume, oh, each time I have segment addition, I'm just adding, then you may get some questions right, but the rest of them are all going to be wrong. So you always want to think about what you're being given and what you need to find and make a problem-solving method from that. All right, now this next one, I'm low on space. So I'm not going to write it out. I'm just going to draw it. This is definitely the bane of handwriting notes because hands are not perfect little printers. So from A to B, we're going to label 2x minus 4. And from B to C, 3x plus 2. Now we're dealing with one of those kind of scary algebra problems I've been telling you all about for the past few days. And this is a big reason why we practiced multi-step equations last week. So I want to think about the little model I drew for example 2. Piece 1 and piece 2 together make our total. Well, in this case, I need to know my total. So the problem will tell you AC equals 48. So we need to know what's x, and then go a step further and find out what the actual lengths are. So what is AB? What is BC? So what I'm going to do is I'm going to take each piece, 2x minus 4 plus 3x plus 2, and set that equal to 48. And now this is looking a lot like one of the problems. I'm going to flip back. Or actually, I'll grab a different notebook to make it easier. When we had our multi-step equations, the one that we had to combine like terms, where we had a bunch of stuff on one side, we're going to have a problem just like this. So we need to combine our like terms. So 2x plus 3x makes 5x, and negative 4 plus 2 is negative 2. And now I have a two-step equation. So if I add 2 to both sides, I'll get 5x equals 50. And I'm running out of room. I can do it. I can do it. And then divide both sides by 10. Or 10. Divide both sides by 5, and you'll get the answer is 10. But here's one case where algebra is quite different from geometry. Usually in geometry, our goal is just a little bit bigger than finding x. Because, okay, sure, now I know x is 10, but I still don't know what the heck the length of this line segment is. So we have to go back and substitute it. So I'm going to do one where I substitute into AB and one into BC. So I'm just going to put 10 where the x goes for each of these and simplify the expression. So here we have 20 minus 4 is 16, and 30 plus 2 is 32. And now I'm able to say, all right, so this line segment is 16 units long, and this one is 32 units long. And a great way to check your work is to go, okay, well, is 16 plus 32 48? Because if it's not, then that tells you you definitely made a mistake somewhere and you want to go back and check your work. So I think this was the most involved example I've worked with you guys yet. And that's one of the nice things about a recorded video. If I went a little too fast, you can back the video up, watch it again, and see if there's something you missed, or just to hear it again. But I physically can't fit any more notes on the page, so we are done with the notes, and now all you have to do is go check out the assignment about line segments, and you'll be done for the day. So it'll be 10 questions long, just like the problems we had in the first week, and I will talk to you guys again tomorrow.